Okay, so we get to the lecture 8, which is on influence of material and process parameters. We hope that we will be able to complete this, otherwise we will continue further. So, a step back means we learnt how to evaluate the crimp characteristics of textured yarn, and we did talk about some of the material characteristics that influence the properties of textured yarn, such as the fiber chemistry and crystallinity of the parent and the textured yarns. So, we continue with this material parameters and see what kind of influence that can have. So, the boundary conditions still remain the same. We are working on thermoplastic multifilament yarns. We are looking at twist texturing, thermomechanical texturing and a single heater machine. Last time if you remember, we said the material parameters would be of the type fiber, fiber morphology, which mean crystallinity, crystal structure, orientation, and other characteristics like specific heat, thermal conductivity, modulus, denier and filament. So, hopefully we should be able to complete at least this. So, we remember that the parent yarn crystallinity should be as low as possible, and after texturing, if the crystallinity of the textured yarn is high, then it will be good for us. We come to crystal structure. So, one is crystalline portion and amorphous portion. We understand crystalline portion is more rigid, difficult to change, you have to give more energy before it changes. But the crystal that form can actually have different structure. You can have triclinic, monoclinic and so on and so forth. So, you can have a different structure. So, some of the polymers like polyester have only one type of structure, crystalline structure. Every time from amorphous to crystalline it goes, it takes only one kind of structure. And some other fibers like nylon, generally depending upon how you are spinning, can have two types of structure called the alpha and beta. And polypropylene, which we said is also a good material for texturizing, can actually have alpha, beta, gamma type of crystal structures. Some materials like acrylic do not really show very highly defined without flaw, without any defect crystals, and therefore, in general their crystalline structures are somewhere in between, not amorphous and not fully crystalline, but somewhere we call it a paracrystalline structure. And polypropylene also have another structure which is in between somewhere called the smectic, that you can have some order, but the whole region is not totally crystalline, and so that is a smectic type of a structure. This term, which is alpha, beta and gamma, have nothing to do with the angle of crystal. You have the angle, it is basically more to do with the stability of a structure. So, you can have more stable structure. So, obviously, the stability, if you define in terms of the amount of energy, internal energy, then all these structures will have different energy. So, they are different stability, one will be more stable than the other, and so as a nomenclature, whatever is the most stable is called the alpha structure. So, whenever somebody says that we have alpha, that means more stable within the same polymer, right. And how do you get? For example, if you draw a fiber, you may get a mixture in case the polymer has mixture of the crystal structures. When you heat set, anneal it, then there is a change, there is a transition, and it will have the tendency to go to the more stable structure, and that would be called an alpha structure. All right. So, all this can be found if you go to the literature and see what type of crystal structure, let us say, the different polymers show. Okay. And you also appreciate that the crystalline structure formation has something to do with the chain folding. One is stress induced where the chains can come together, but when you anneal and give freedom, the chains can fold over each other, and so wherever there is a possibility of easy folding versus difficult folding, so you will have a different kind of structures. For example, you may be aware that there is something called normal spinning of a melt spun yarn or high speed spinning. So, when you do high speed spinning, the time available for getting down to the nice beautiful structure would be less, because it gets cooled down to a solid state. Once it becomes solid, then obviously changes become more difficult. So, sometimes whatever best could have been done is done. So, you can find various structures. So, now let us say if the question with us is the texturing. So, when we have a parent yarn, would it be advisable, if you have a choice, that your parent yarn should have stable structure, which is the alpha, or should have other than alpha structures which you may like to have for the parent yarn? Right. So, you want less stable structure. So, as far as the parent yarn is concerned, you want less stable. Why do we want less stable? Because we said this whole process of texturizing is partial melting and recrystallization. So, if you have a less stable structure, it will be easy to melt partially, so that molecular chains become free and they can go back to another structure which may be more stable. And so, it is obviously easy to conclude that in the case of textured yarn, obviously finally you will want stable structure, that is more stable structure. So, that means you have another parameter. If you have a choice, you can think about it and utilize. And people do get smart if they know more about it. Then orientation in a fiber or a filament is defined, that if the various segments, phases like crystalline phase, amorphous phase, or the molecules, if they are more oriented towards the fiber axis, along the fiber axis, then you say it is more oriented structure. Okay. So, if you draw, the orientation improves. If you heat set, the orientation can go down, because you have given the freedom, and freedom means that you can take any position which the molecule or the segment or the phase likes. Okay. You know how to measure orientation in a fiber? How do we measure orientation? Yes, so birefringence is one method by which you can get an overall orientation. If somebody wants to say, well, I want to know what is the level of orientation of the crystalline phase and what is the level of the amorphous phase, can you define? Can you do that also, segregate them? How do we do that? How do you do that? Anyone else? X-ray diffraction. So, from the X-ray diffraction you can possibly get the orientation of the crystalline phase, and then you can have a relationship. From the birefringence you can go and segregate amorphous and the crystalline part. So, you can find an orientation of a fiber. So, you can have the same thing, orientation of a parent yarn if somebody says, well, you have a choice, would you want the orientation of the parent yarn to be high or low? So, what do you say? Low. Okay. I just note down, you are saying low. So, how many people believe that should be low? 1. So, others do not believe it. You can appreciate when you draw a fiber, you improve the orientation. In what way it will help? If you have higher orientation, what are the general properties which are likely to be affected? So, tenacity may be higher, modulus could be higher. These are the properties you can think it will be higher. Why this happen is because the stress, the level of the direction of the stress is along the direction of the fiber axis or a yarn axis. So, all the entities try to orient themselves toward the direction of the force, right, the tension that you have. In the case of texturing, what you are doing is you have taken a fiber, and if there is any stress in the yarn, which should be, the stress is in the direction of the yarn while it is being heated, but the filaments are twisted. The filaments are not a parallel bundle while they are being heated. And therefore, if you look at an individual filament, the direction of stress may be oblique to the direction of the fiber axis, while the filament is being helical, the yarn has a direction. So, when you say this is the yarn, but the filament is like this and the stress is in this direction. So, a filament which is just moving over, it experiences stresses in the direction which is not in the direction of the filament axis. So, now the stress is in different direction, and what is the role of a stress? To orient all the entities towards the direction of the stress. So, when you get back and get a textured yarn, the textured yarn is going to be tested when there is no twist. You remember, a textured yarn is a parallel bundle, okay, of twist lively filaments which have no overall twist. So, when you are testing, it will be after 0.1 gram per denier, it will be a parallel bundle, and now you will be testing the orientation, let us say. So, what value you will get? It will be reduced even if there is a stress in the yarn, because the filaments are in a helical position. So, if we can make a statement that texturing is a disorientating process, whenever you texturize, whatever you do, the orientation in the filament is going to reduce, it will not increase. Unlike the case when we said the crystallinity can improve because you are going to a more stable state. Crystalline structure can go to an alpha state, which will be more stable state, but after texturing, the orientation of the filaments is going to go down. So, you can say it is a disorientating process. So, it is going, everything is going to disorient. So, when something disorients, so you are quite sure, as you said, the tenacity as also the modulus of the yarn is going to be low, will reduce. So, the common sense therefore says is, well, whatever it is, Crystallinity we have already handled. If suppose we have independence, crystallinity is constant, orientation is high or low. So, we may say, well, we may not go for a low orientation. We may like to have a parent yarn with as high orientation as possible. It is again a choice. So, it's a slightly different way to look at it, because you will still want, although we said tenacity at break of a textured yarn may not be very important, but why do you want to reduce it further if it is possible for you to have better, because it is not going to give you too much of advantage, it is only disorientation process. So, we look at some other properties also, which means specific heat, thermal conductivity, modulus, etc. So, these are also the properties. They would play some role in heat transfer, heat storage, and of course, flexibility, etc. So, specific heat is one, it is specific to the material. You take polyester, you take nylon, you take polypropylene. If you have been given a choice, if you have no choice, then you have no choice, but if you have a choice, what would you want? Specific heat of a parent yarn to be low or high? So, there is no confusion here, because that would means you will require less amount of energy to raise it to a certain temperature, which is the optimum temperature. Because the temperature has to be optimum, you have to go to that temperature, everything is a room temperature. So, obviously you like to spend less amount of energy to go to the same temperature. So, there is no confusion here. Thermal conductivity. The thermal conductivity is a heat transfer, because the heat is being transferred either through the air, maybe by convection systems, or through a contact heater, which is a metallic system. From that to the fiber, the yarn has the heat has to be transferred. So, it is obviously interesting if the thermal conductivity is high. You get surprised that the conductivity of different fibers is different, like polypropylene has a poor thermal conductivity, polyester also has. Now, how does it matter to us? Well, maybe we will have to think about when you are giving some time, because you can't change temperature, optimum temperature cannot be changed very easily. Time, maybe you can think about it, or the length of a heater. And thermal conductivity also is important, not just during heating, but also during cooling. So, in one case you have a heater which is a higher temperature at a higher temperature, and the heat is being transferred to the fiber. Once the filament exits the heater, it must get cooled down before the twister to a temperature which is below the glass transition temperature. Otherwise, whatever you have done can be undone. So, this property could be important, and if you cannot obviously handle, you say, but somebody has to texturize polypropylene. So, you have to texturize polypropylene, you can't do much about it. Then you have to think about the times, they have to think about the lengths of the heater, the length of the cooling area. So, all that will have to be worked around based on what kind of a material. So, finally, if we say that we want low crystallinity, less stable crystal structure, high orientation, low specific heat, and high thermal conductivity. All right, this is how we work. So, there are three other things which are related to some of the properties dimensional or mechanical properties of the yarn. This is a force, a resistance that will be offered. Let us say you have made a helix. So, is the force when you stretch or after stretching it wants to recover. So, whenever you stretch you will experience a force, right, the resistance. So, that kind of a thing. So, you made a textured yarn and obviously you are stretching. So, there is a resistance being offered, and empirically they have found, the group Al-Bihari and et al. Found that it is related to the modulus the Denier, which is filament Denier, individual filament Denier, and Denier total of the yarn. Okay. And this is diameter of helix. So, there is something called a formula derived from fundamentals, okay, and you get to an equation. The other way is experimentation. So, when you say empirical equation, that means people have done experiments and then they, after a large number of experiments, they find that this is how the things behave, and this is how we would like to understand.
What is C here?
All right, that is a good one. So, this is some constant. See, this constant will change based on the units that you take in meters, centimeters, inches, foot, pound, whatever. So, this constant will change. Now, the question that remains is why the modulus of the yarn, whichever you are using, would have anything to do with, let us say, this force, the resistance to deformation. So, what do you have? So, you may be having a thin helical system with a thick, I am surprised that actually has been, it looks like that, it may not be thick. If you have a, what we are looking at is a modulus of a material which is of any type, and what you want to do is extend, stretch. So, which modulus are we talking about first? Can you just guess? Obviously, it is a textured yarn. Without textured yarn, there is no question of a textured yarn also. Which type of modulus are we talking about? We have right. So, this is your textured yarn. So, which modulus are we talking about? Important thing which you must remember is that this test, when it is performed, obviously it is like a tensile test. You can have something, you can try and measure here, or you can measure here, where, which one we would like to measure. Right. So, it will be interesting that the stresses that build up here are the ones which are the property of the basic material. This is only crimp or helix opening. This area in the beginning is the opening of the helix, right. So, the opening of the helix, and so that is in some way related to what sometimes we call as a low strain property. So, crimp opening and going back to crimp. So, what you are saying, there is a crimp which was there, maybe a helical structure, and after putting a stress it opened. Then when you leave it, it goes back to the crimped state. Does the filament in during this process actually get extended in length? The helical structure, you put some load, the crimp is gone, and then it's come back. Whether the length of this filament changes during this process or no? No. So, this opening of crimp and coming back to the crimped state, there is some deformation, because it was in this state and now it is a flat state. So, there is a deformation, but this is low strain, low deformation, low strain and low deformation condition. Which tensile property of any material is related to low deformation?
Elasticity.
Tenacity, extension break, modulus. Which property is related to low deformation? It is modulus, because you are looking at a very low deformation and want to say what kind of stresses build up, all right. So, this stretching and recovery, which is what determines or which is what will finally get to you a value called the crimp rigidity. If this force of the resistive force is high, then it will recover well also, unless some break occurs, We are hoping that damage is not occurring during this process. And so, this force is in some way related to crimp rigidity. Okay. So, if someone has said that it is actually related to this F is proportional to E, was he wrong or right? So, it is reasonable, because this whole thing is related to the modulus, because modulus is a low strain, low deformation property. So, if you try to relate this force with tenacity at break, you will find almost no relationship, but here it was true, all right. So, that means if you have two types of fibers almost handled in an optimum way, one of them actually has a high modulus and other has a low modulus. So, you can expect similar results in the crimp rigidity. For example, between nylon 6 and nylon 6,6, okay. Because of the molecular structure, let us say the best possible state that you have, a crystalline state, which is alpha state. In that case, what you have is there is something called an anti-parallel structure. You have a molecule, one molecule, let us say in this way, where you have CH2, CH2, NHCO, and the other hopefully this way. And if you are lucky, let us say this is CO and this is NH and then maybe CO somewhere, etc. If they come very close, then they make hydrogen bonds. So, intermolecular hydrogen bonds, if the possibility of forming intermolecular hydrogen bonds is high because of the molecular structure itself, then the modulus of that particular fiber could be high. So, generally we have seen nylon 6,6 gives higher modulus compared to nylon 6. Polyester also gives higher modulus because of the aromatic ring that you have, it gives rigidity, extra rigidity. Polypropylene may have low modulus, although you must remember this modulus is something which you can manipulate also. If you do more drawing, the modulus can change, but then if you do more drawing, the Denier changes. Then you have a different parameter come into play, but nevertheless. So, you can try to do one exercise at home to draw anti-parallel structure of nylon 6 and nylon 6,6 and check by this kind of geometrically representing these molecules, can you somehow prove that one of them would probably make more intermolecular hydrogen bond than the other. So, this exercise you may like to do, you can. So, individual fiber Denier or filament Denier, which is represented there as a small d, how is it related to the F? How is it related to F? It appears this is related to Denier directly proportional. Why? I am just trying to draw maybe a thicker helical thing. You want to stretch this versus this versus this, which will be easier to stretch or which will offer more resistance? The one with right. So, this also appears that whatever we have stated is correct, because you can appreciate when we are opening also small deformation, but what you are doing is something which was inside the curve versus which is outside the curve. So, when you deform them, the larger is the distance between these two surfaces, the more is the force that is required to unbend the crimp. and if nothing changes, then it will also like to go back easily. If it is very fine, then the resistance offered is less, because at least bending is happening or unbending is happening. So, bending unbending situation, if the distance between the two surfaces is high, that means the diameter is high. Denier high means the diameter also must be high, and so this is what is the reason why you find that this particular factor also is proportional to the force resistance. So, total denier would mean that we are looking at changing the things maybe by number of filaments. Instead of 20 you have 40, keeping the small d constant, and you can still increase the denier. So, in this case what is expected? If I increase the total denier of the yarn, what do we expect? The force resistance to go high, right? So, you expect it should also be that if you increase the total denier, the force will also increase. This is what we mean, right? So, they did experiments, because they say this is an experimental formula, empirical, and what they found was when you increase the d, F goes down. So, this is, it did not happen. It was interesting for them also. So, the d can be increased by increasing the number of elements, or it could be increased by increasing the individual denier per filament. Anyway, but whenever they increase the total denier, they found the stretch potential, if you can call that also, goes down. What do you think could have been the reason? Yeah? Cross-sectional area, let us say, is all circular fibers to begin with, right. So, you are looking at diameter of a fiber filament, right. But they found one interesting thing, that whenever the denier is high, the diameter of the helix is also high. So, if you have two situations where the diameter is this of the helix versus this, in your own opinion, which one will be offering more resistance if the individual denier of the filament is the same? The one with the larger helix or smaller helix? The smaller helix therefore is going to offer more resistance. So, what they found is that when you change the capital D, that is the total denier, you cannot independently change this independent of the filament, the helix diameter. So, that also increases, and they found that is proportional, inversely proportional to the square of the helix diameter. So, it actually becomes very easy as you keep increasing the diameter. And so, F is not proportional to D, but was found to be proportional to D over A square, and therefore, if you only look at D, then you get the inverse relationship, and that is how this particular understanding came from the point of view of the textured. So, one more thing obviously you can always remember is this F, as I said, has something to do with crimp rigidity. because you will, it is easier for you to do texturization, and after that you measure the crimp rigidity and then correlate it with whatever you did. You change the individual filament denier, you change modulus of the material, or you change the total denier, whatever you want, all that you can look into it. So, we summarize here. There is the chemistry of the fiber, also the morphology, which is crystalline, crystal structure, orientation, and other properties of the material which are related to the heat transfer, heat capacity, the modulus, the denier, and the total denier of the yarn, textured yarn, and this is how all this material characteristics. So, next time hopefully we will look at the process parameters and their relationship.